Okay. Ladies and gentlemen, I would like to welcome you in our series of seminars. Today, it is our pleasure to welcome Professor Leonid Fridman, professor at the National Autonomous University of Mexico, and one of the world's leading experts in the sliding mode control. He is internationally recognized for his seminal contributions to high-order sliding modes and robust control theory. And today he will introduce to us modern sliding modes, maybe 5 generations of sliding modes. Please join me welcoming Professor Fridman, and thank you for being here, of course.
Thank you inviting me. So I'm really happy to be here because something like a couple of years ago, my university, which is the biggest university maybe in the world, but it is in Latin America, less than one campus, we have 320,000 students. 12 bus lines, 2 metro stations, and 60,000 of professors. So it is national, let's say, honor. And they are trying, let's say, it started from minerals to minor and why? Because Spanish people came to Mexico to bring the gold. And finally, they started from mining school. And then now we are 500 years old, but we have different stages of development. And the last start was around 50s when people started to understand that industrial revolution came to Mexico. So, and to tell something, my wife, she has 86 cousins. This means that he was born in the family from the mother's side, and he was 10 children from the father's side, 14 children. And now, unfortunately, my postdocs and PhD, they are not sure to tell which is what. That's how the number of people. So I came to Mexico with this moment because it was a young country where the leading age was 21, and the government was not like actual. They understood that to avoid the problems, they need to invest a lot in the city. That is why they offer good opportunity for the professor will be able to create scientific schools. And we four from the same lab was going to Mexico, because they offer us more or less good conditions. We will not be young. We will not be young for immigrated in 46, but it might last like 25 years. I generated 27 PhDs. So it is an army, and together, all together, we have generated around 120. And our students generated other 50. So we've made a big army of children. So now, writing here, because the universities in any big country, even it is big, give the saturated. Now, in the stable up, and master degrees, bachelor degree, master degree, PhD for student, and the master was a bachelor student. Can see that there is no position in Mexico because good postdocs cannot find something. So I think that your country, I mean Arabia, now is a similar situation. And so maybe I see that in this university there is good injection of money as well as in college. So that is why one of my one of the goals for me, because I'm let's say not old but still strong. I'd like to inject something here, and I see here new faces and the new young people which still have a hungry, have some hunger. They like to make some more science, and that is why I decided to come here in order to make here also the group, because it is it is my third place that I'm searching for the third place I can make a group, because I already make a group in France, in international chair in France, and I've already made another group in Austria. And now maybe my will is to do something here. That is why I came. That's the main idea, and I would like to see. It is not just a seminar for me, because I've made it in 70 countries. It is something. So it is not a big goal for me to go to the new place to make a seminar. For me, is just a need and maybe a wish to have collaboration. And if it will be so, I'll be happy. And if you, so I'm not searching for just one day conference. I'm searching for a long-term collaboration. That's a big deal for me, because I feel that I still able to do something, and I needed some kind. I feel myself some kind of colonel, and I need a soldier. Sorry for that, but let's say it is a strange comparison. So do you have something to move forward? There is something to move the slide.
And you can use your finger to take it. This. That is great.
Okay, let's say okay, it doesn't matter. If it is so, I'll do. And just not, it is not suitable for me. So what I do, what I will speak about my work. So my father, which was also professor of math, he told me, the only you can share with your student is the law. That's what I'm trying to do. So let's see. You already know that I was working all of my life in sliding mode control. So it's not. Okay. What sliding mode control is? Imagine that you have your freezer and you wake up in there. So what happens? You see that you hear that compressor is what doing. What compressor is doing? Switching on and off. Okay? So why? Because you have a corridor of temperature. And if you have corridor of temperatures, according to this, your compressor switching on and off. So does it important the external temperature? No. That's the point. So now you see this table. I'm perturbing it. Why it doesn't move? Because there is a drive friction. What is drive friction? Is sine function. You cannot see how it switches, but it is same function. It's discontinuous. If you model the friction as a linear, will you stop or not? For sure not, because you will have asymptotic convergence, isn't it? You will have minus kx, so as bigger as the gain, faster you will go to zero, but you will never reach. So your car will not stop. That's the point. Without right friction, your car is not stopping. So this means that really control sine function. It doesn't work. So without this, does not work. So return to our refrigerator. So what happens? You will make the corridor smaller. What will happen with your compressor?
Frequency.
More frequency. So now imagine that you have 001 corridor. What happens with your compressor? Oh, because he cannot switch with such a high frequency. It is clear. So, and then you are understanding what's the problem here. First of all, it is a natural control because people started to use it for, let's see, for example, for level of water, something like that, 1,000 years ago. Other side, from the other side, in mechanical system, it is always a way why it works, because you cannot describe why the car is stopping without discontinuous motor. So, in 50s, people was using controller to track the trajectory. And for example, if you are trying to move some airplane, you cannot predict the weather. That because the probations, but you need to follow. The same is the ship, the same is the cars. So they started to do it, and they are telling, okay, we'll switch, run 1, 2, 1, 2, 1, 2, and we will go. That's how it works. The point is that the requirement of precision becomes to be more better. And also switchers in controllers, the frequency of switches. Every year you can switch 1 order better, 2 order better. So can you do here different theory? No. You can go just with code. You can tell, okay, suppose that the frequency of switches is infinite. In 50s, all of control theory was based on frequency domain. You know, body diagrams, compensators, and story like that. Can one imagine that you can do the theory with infinite frequency? No. It is only crazy mathematicians. So that was a key point. So from the viewpoint of normal control theory, it's crazy. From the viewpoint of mathematicians, from the viewpoint of the nature of mechanical system, not. So that is why what is necessary to do. It was necessary to develop first specific mathematics to deal with this continuous with equation with the continuous fraction side. Why? Because in the standard way you cannot explain nothing. Because first of all, what people are teaching from differential equation and or some of you maybe know Halil book. If you know the book of Halil, what he is telling, we are working with Lipschitz system. Does it really control Lipschitz? It doesn't. It is not Lipschitz. You need to deal with special mask. So that's what it is. So how it works. Because I need to go to slide to slide. So okay. Then the first step has been done. Control L. Okay, good. It was the first Congress, IFA Congress in Moscow, 1960. It was a clever guy called Professor Filipov. And he understood what happens there. He told, guys, you see, this is a table. For table, doesn't matter which calculations I'm putting before I will be more than right frequent term, isn't it? I need to make a strong force to move it. Before, it doesn't matter. So what happens? Maybe the chair, the table is so clever, she is able to identify perturbation and to return it like third law of Newton is telling. No, he is not clever. So what does it mean? This means that the system should have the same solution for all of perturbations. So that is why you have to work not only with the equation, you should to work with differential inclusion. That's the difference, because you don't know what is in brackets. When your car is stopping, it doesn't matter if me is inside or if you are inside. So for car, it doesn't matter. It will stop, isn't it? If it is so, you need to work with inclusion. And that's the main word here. What is the main word? The good controller theory should work on inclusion, because you never know the model. The people which are very close, you never know the model exactly. There are some so the same story is here. So what was the main idea of Filipov? Filipov told, you have equation with discontinuous right-hand side till the moment you will stop. Because if with continuous right-hand side, when you will stop, you will not have equation. You will have because you don't know. So that is why he told, okay, we need to consider equation with discontinuous right-hand side, which converge into the inclusion. I will not go to mathematical details. I wouldn't like to charge too much here. But I will return to the family example. What he told, okay, guys, I have a circle. I have the goal of the family. And what happens? This is me, and this is my wife, which sometimes they are contradictory. It happens. So what happens to follow the goal of the family, to form well the children? You need to find a compromise. How to find it? He told, okay, let's make a convex closure. So you need to make a linear combination of this vector and find the way to be in tangential subspace. If you will be in tangential subspace, It is a compromise allows you to pull the track. The track is so. So that was very clever explanation how to track. You need, as well as the family, you need to find a reasonable compromise and which does not affect your children. That's the same story. Okay. Now, is it engineering language? Not. For sure. Imagine it is 60. People not all of the people was agree that you need to work in the state space. For example, you know that Kalman published his famous paper in transaction of Mexican Mathematical Society. Why? Because people didn't accept his paper for IEEE transactions. That is why it is the most cited paper in all history of Mexican Mathematical Society. The first paper by Kalman. That's the story. The same story was here. So it was necessary, clever engineers, which were be able to translate this crazy stuff into normal engineering language. What control engineers should think? They should tell, okay, guys, I'm control engineer. I need to form the signal, control signal. How to form control signal to follow the surface. And that was two guys which was able to understand that. This is my scientific advisor, my scientific father, and this is my scientific grandfather. Professor Rupkin is my mentor, and he was a student of Professor Emilianov. This is photo dated by 46, and this is a recent one, but both have passed. But it is more or less 2050. So what they've done? They formulated two principal ideas. They told engineers, don't fly. You need to follow the surface. Okay, what you need to find a way to be in tangential surface. What you do? You have some restriction, and you need to follow such a restriction. What you need to do? You need to differentiate this restriction according to this equation. So what you will have? You will have this one. What's that? That's algebraic equation with respect to you. He told, okay, let us find equivalent control allowing us to slide. If we will stay on the surface, we will not go outside if we are here. What is the condition? Condition is just to nullify the right hand side. If you nullify the right hand side, we will not go out. So he don't forget about conclusions. It is just simple algebraic. No more. And that was a first step. Okay, good. But what happens? It is just for single variable, or maybe for the vector variable. But the point is that, okay, imagine that mechanical system you have, and you'd like to stop velocity. So what is to stop the car? To stop velocity. Okay, is it good? Okay, we will stop. But what's the point? The point is to stop before step, not after. Because if you stop after, it doesn't work, isn't it? So you need to the same to control two variables with one control. What to do? He told, okay, imagine that you have a government, and in the government you have every time less policemen than people. So what you need? You need the following. You need to write a constitution, and then to ask the policeman to follow, isn't it? So what he told, okay, let's write a constitution. Choose the surface you'd like to follow, and then call policemen to enforce the other people to follow it, because the majority of populations will live according to the constitution. So that is why this is a main idea of sliding mode control. You can see it here in the logo of my lab. So what you are doing, you are first attracting to the surface, and in the surface you are invariant with respect to the control. This example. This example is an example of mechanical system. What you can have here, you have here standard first equation, position, velocity, and derivative of velocity is a force, and here is uncertainty. If you have an uncertainty, and uncertainty is bounded, what you need to do, you need to ask the policy, and the policy will force you to follow this surface. Then you will attract to the surface, and you will follow it. Good, perfect. But the problem is, policemen, they are not every time correct. If you are victim of them, they will push you, and each step you cannot go left, you cannot go right. What happens? They will tell, okay, guys, for such a small salary, to work too much is not too good. So what is the solution? Or the policemen will stop, or they will kill the victims. No chance. So what does it mean? This means that there are two options here. First, you have to take care on tweeters, because if you will switch too fast too strong, you will lose plenty of energy, and your actuators will be destroyed. Otherwise, you will destroy the plant. It is even worse. So that is why. What is the art of sliding? It's beautiful. Why? Because you are not dependent on perturbations. It is bad. Why? Because you need to take care on policemen or theater, and you should be careful with not destroy the plant. That's the story, and that's the art I've tried to do all of my life. That's the starting point. So, of course, it was designed for vector cases. What happens next step? The next step was Professor Brana Draženović. She also passed away last year. So what happens here? What happens here is the following. You see, we have one perturbations here, but the perturbations can be not belong to the span on vector B. So what does it mean? This means that, for example, you can control just part of variables. For example, if you have two links robot and you have a tweeter showing here, so the perturbations are here, you cannot control this. So that is why Mexican are telling you are unable to keep two watermelons with one hand, or here, or here. It is impossible to control both. So that is why if you have perturbations which are not depending on which are outside of the span of input matrix, you cannot compensate all perturbations. And it was because it is 69. In 69, people was romantic. Oh, this control is able to compensate all, not all, just a part. And it is clear. You cannot compensate what you are unable to reach. If you are able to reach, you can talk. You cannot compensate what you are unable. That's the story. Then Professor Lukyanov made the general way how to do it. And we thought, okay, how to design sliding mode control. You need to play billiards. How you are playing billiards? You have a ball and you have another ball, isn't it? So what you are doing, you need to calculate precisely where you, in which place you can touch the other ball, and then you are actuating, isn't it? So what he told, okay, let's transform the system in two subspaces. One, which corresponds to the B matrix, which called matched, and the other one which called unmatched. So first ball, if the system is controllable, you should be able still control x1 through x2. And x2 makes the sliding surface in such a way that x2 will be some function of x1, which allows you to control this ball. So here x1, x2, here is x1. So what I'm doing, I'm actuating over about x2 to have a control so about x1. So and that's called regular form, and it is one. It was much more before that papers of Isidori and story like that, and he told, okay, let's do a regular form, and we will do a control of system of any order. That's good. But the problem is still that we cannot, to do that, we need to split the system, and it is every time a big job. So then, you know, the life is, in that time was simple. It was just two poles, Russians and US people, and Kennedy told that Americans will be first on the moon because they lost to Gagarin. The same story was here. So Professor Leitman group, it is all here. They've produced the new controller. It looks crazy, but it is, from mathematician, is very clear. They called unit control. What is it? It's not a sign function. It is sign function when you have just dimension one. Here is arbitrary order, and if you will tell that it is sigma 1 and divide it for norm of all of sigma, so you will have the control whose norm is unit, but it will be discontinuous at 0. Why? Because sigma is discontinuous when you are at 0, but it is vector. So finally, what they've shown that in finite time, they will not have the estimation which we have standardly for exponential stability. They will be able to estimate V dot through square root of V. So this means that they will converge from finite time. So, what is the advantage and disadvantage of two controllers? One of them, which is unit, is discontinuous only in a region. The second story is that all components will converge in finite time and simultaneously. In relay control, they will converge in finite time if you will do the things well. But the problem is that they are not converging at the same time. But what is disadvantage? Disadvantage is that sliding mode control is often used for fault tolerant control. Why? Precisely because it is very robust. Yeah. So what you need to ensure that your system still works is one channel will fail. in scope. You need to control channels one by one. This control controls all of the channels simultaneously. If one will fail, all control will be failed. That's the difference. So now they made a little bit more. What they told? They told the following. Okay, why I need sliding mode control? We have just we have perfect trajectory. For example, we need to put this, we have ideal trajectory and we need to follow it in the space. Now it's very important for military reason because we are making very precise 3D models in order to avoid obstacles and stuff like that. You need to follow precisely the curve. Otherwise, it doesn't work. And what was the problem of sliding mode? You're reducing the space. You cannot avoid the stories. You will have. So you need to follow to track the trajectory. And they offered so-called integral sliding mode. They told, okay, let's divide the things. Linear standard control, which generate you in, let's say, nominal trajectory, you will follow it. And then add something, and this addition will ensure you what? This addition will ensure you robustness with respect to perturbations you didn't take into account. So in such a way, you will have the story that your sliding surface will be virtual because you added some dynamics into the system. And in these additional dynamics, you will fight only against of uncertainty. That was an invention of American people. And then my professor, Professor Rutkin, made an addendum. He told, if we know initial condition, we can start to follow the trajectory exactly from the first moment.
देखो ना दे नजर नहीं आ रही है देख लो ना
So and finally what happened? It was all theory done under the condition that we don't have a chat, but we do. So why we have chatting? Because we need to act very fast. We need to act with infinite gain and with infinite frequency. So what we need to do? And it was a start for my PhD work and for my friend's PhD work. We need to make Lipschitz control. At least Lipschitz signal. Maybe control will be not linear, but the signal we are generating should be Lipschitz. Why? Because if it is Lipschitz, it's not infinite gain. Perfect. If we will do so, we will be able to not avoid completely the problem, but to make it much smaller. That's what happens. So that's me and Professor Levant, my friend. We've done maybe first steps in higher order sliding mode together. Now he will also retire. So what we've do, what we've understood? We understood very simple story. If we do theoretically really control, it will work perfect. But there is one policeman. The policeman is actuator. So if here relative degree will be 1, here relative degree will be more than 1, at least 2. Good trick. So what to do here? So what we need to do? We need to ensure the same motion, even if there is some extra dynamic. So that is why we need to converge not only to signal, to variable we need to follow, but also at least for one of its derivative. So that is why you see we were young. So, and we've designed so-called controller called twisting. We've twisted So what is it? It is a controller which works very logical. You need to put it with people in the angle, what you need. You need first to overcome breakage. And then when you will reach the angle, what will change? Your velocity will change. Your acceleration will be changed, but not velocity. So that is why you will pass and then go. It looks like a periodic system with the focus. So you will make rotation, but what's the difference between standard linear system and this one? You will converge the time between switches will form geometrical progression, and you will converge in finite time. So this means that you will, for a finite time, converge not only to x1 equal to 0, but also to x2 equal. That's the point. So, and here you see the difference. The difference is, okay, here is a standard sliding mode. Here is a second order sliding mode. So you will have what? You will have finite time convergence. You will follow. Even there are perturbations here. And this is a phase portrait, and here is a comparison. The comparison is that, okay, in the first order, you have a surface and you will attract to 0. In the second order, you don't need a surface, you will go directly to 0. But if you will see control signal, it will be even more chattering. So you will ask me, why you've done it, guy? The answer is here. Imagine that we have first order system and we need to put here Lipschitz control. What we will do? We will put not this control, not standard sliding mode control. We will put integral from this control. This control I've shown you before. It was for the second order sliding mode. So what will happen here? This is discontinuous. U is Lipschitz. With Lipschitz U, what you will have? With Lipschitz U, you will have not only sigma 0, you will have sigma dot equal to 0. So, and that was a solution to the problem. Of course, your perturbations should be less strong than your policemen. So what does it mean? If the policemen are weak and the victims are stronger, you will put the policy off and go. No? So that is why, if you like to have Lipschitz controller, please deal also with Lipschitz perturbations. If there will be discontinuous, you cannot do nothing. That's the point. Yesterday, one guy asked me from your class. He asked me, to which level we can fight it in the chat? And I answered, till the level of perturbation. As stronger your perturbation, stronger should be control. If the perturbation is a little bit weak, you can also make convergence. That's the story. You cannot ensure with the weak policemen a good performance. That's clear. So, and then it was precisely the revolution. In which consisted a revolution? A revolution consisted in the following. You see, to realize this controller, you need what? Derivative. So you need first to differentiate sigma to know that, and then you need to realize it. So the next question is how to substitute discontinuous control with continuous one, but without usage of the derivative. And the answer was very strange. PI. Why PI? Because if we will do our PI, not the PI you are normally seeing, what happens? Let us prepare a special control, special linear, special proportional part in the way of sliding mode or homogeneity. So what is it? It is proportional, but proportional to the square root. And here is integral, but integral not from x, from sine of it. It allows you to do the same job. What is the same job? You can find with this Lipschitz signal, with any perturbations, which are Lipschitz. Because this signal is Lipschitz. Here is a derivative not more than 1. So, and here it is a bad term, because even it continues, because what is it? It is parabolic function like that. But what is bad in this parabolic function? Here, the gain is infinite. You see, it is square root. The derivative of square root is 1 by square root, so 2 by square root. So that happens. So, but this was a first and very simple answer to the challenge. And you see the same story here. First generation, second generation, third generation. Practically no chattering. The same story. You can choose a surface, you can approach to the surface practically without chattering. It will be second order chattering with respect to discretization, but not the first order. And you see here is the first order. That's the difference between here and here. It's the same system. Okay, so, but it was not a main, maybe not a main, what we've done. It turns that we've tried to make simultaneously observers, because people, when they are doing controllers, they are doing differentiators. So what happens here? Here, you see, you have a signal, and you need to find its derivative. So what you are doing, you should suppose that derivative is at least bounded. So you are making observer in this form, x dot equal sine of E, and E is error between measurement and your observer. So what happens? When T will be more than F2, you will have a sliding mode. And so this signal will equal to F dot. That's good, but this signal is oscillating. So what happens here? You need what? You need to differentiate the filter. But because there is a lot of filtration. Now, the same story, but you can suppose that the second derivative is bounded. If the second derivative is bounded, you can use the same PI, and you will reconstruct derivative without perturbations. You will have theoretically exact value of derivative without filtration. So you will tell me, Guy, you are using infinite gain here. Yes, I do. But what is proved? That it gives you better possible approximation of derivative in the presence of bounded nodes. And it's mathematically proven. It's proven by Kolmogorov in the 60s, the level. And they proved that it is also the same here. That's it. So we've done the best possible differentiator. And on this base, we've constructed observers. I feel that my time is going to finish. That is why I will tell you just some words how it works in general situation. In general situation, you need to do something for arbitrary relative degree. And this is kind of controller, for example, for the third order sliding mode. It looks crazy, but you see this is special choice of degrees allows him even for the third order to converge in finite time, but it is discontinuous. And here is the other family of such controllers. But what's important here that you are able to come, because let's say here you need to adjust the controller for third order system. You need to adjust just one variable, and this variable is an upper bound of your perturbations. So the same is with arbitrary order system. To control arbitrary order system, you need to adjust one constant. So imagine that if you have the system of dimension 5, in standard way, you need to adjust at least 4 gains. Here is just one. And you will have theoretically finite time conversions to a region in finite time. The same has been done with observers. Here, to realize it, you need derivatives. And here, in the same way, we've done differentiators. And finally, you are able to construct the controller of arbitrary relative degree. So then what happens? You have gray box. You never controllers what they are, control engineers what they are doing. They are trying to control black box. What you need to control black box, I don't know, it's black. So what I need to control is gray box. What I need to know about the box, if I would like that all variables will go to 0. In this case, I need to know 2 things. First of all, a relative degree. If I know the relative degree, I know the output. I can differentiate it in the best possible way in the sense of Kolmogorov. And I will return my controller. And I can ensure that in finite time, I will convert all of the, not only output, but all of its derivative to 0 under the condition that I need to know upper bound of the system dynamics. That's so I need to know about gray box 2 things. First of all, relative degree, then upper bound of system dynamics. Finally, what I've done, I've made a controller for this gray box. If I will have a noises, and I will have it, I can realize it with best possible approximation in sense of Kolmogorov. So, and then what we've done in the last 10 years, the main point is so-called continuous controller. So means what we've done. We've done the following. We've made a so-called, for example, PID-like. What does it mean, PID-like? PID-like means like the following. This is p-term proportional. This is the derivative term is velocity. And this is integral from position. So it's PID, and it converges to for the system of order 2, not only for position and velocity, it converges to also acceleration. So that's my life. So the only I would like is to share with you a classical sentence. I do like it, and I like maybe can I show it or I need
Yeah, we can show it.
please. So which just one slide. So this is it's already open. Yeah, sure. Please. I need to share this screen. Oh, yeah. What I like. Let's say a book. Okay. I will share with you the theorem by Dr. Leitman. He told that if someone will tell you that his method is better than the other, yes, you see, it's Leitman theorem. He is telling there doesn't exist a best method. That is one which is superior to all other methods for solving all problems in a given class of the problem. He told by contradiction, because every time you need to make, you are able to make something which is better. But those who believe or claim that their method is best one suffer from alliterative application, ignorance of or arrogance. I would like not to tell that my method is the best. I would just like to present what I presented, and you can ask me the question. So that's the final verse. Maybe I will share some videos from my lab, but it is just a will to say, to show that even people they are thinking that infinite gain is not good. But we will discuss it later. So very funny experiment. It is very famous. Carpengal, and it is unstable. But please try to make it as stable. You see, we are making here is we are trying to track here is A. So yeah. Here is a model of the crane on the ship. You have waves there and wind. So, and imagine that you have a container with 20 tons. So it will be a funny story to control it, because if he will oscillate, don't worry, that's what we are doing. And then we will switch control off and you will see Columbius. Here you see it's controllable. And now without control, it will be. It is very That's because it was too long. So you see here, fractional pendulum. And here is very interesting phenomenon. It is linear control. And you see that it is not stable enough. And it requires a lot of energy. Here is a continuous sliding mode control like PID-like. So you see practically no movement, and it is stable. Here you are using much more energy. And here is middle level controller. I will not speak about it, but that's how it works. So, of course, sliding mode controls, they started from power electronics, because when you are switching the high frequency there, converters, story like that. But I made such video just to show you how it works, because if I will show you boost converter, what you will see just a graph. It is something failed. So my time is finished. I'm very sorry for some technical problems, but finally I think I tried to say like this. So that's the pendulum. Is the person which nominated me for IEEE fellow. So I'm very, let's say, I was very great. And I don't know if you will remember this, but how we are making oscillations. Actually, it is unstable. You see, it is very difficult. When he visited me in my lab, I understood that he likes tequila. You know what tequila means? So, and I've sent him as a great, as a gratitude, the way how my pendulum supported the bottle of tequila, but I'm not sure that I'm able to show it here. But believe me that this pendulum supported the bottle of tequila. Like approximations. Thank you. Here is the animated show inside instead of scientific presentation, but if you like to know something more, please contact me.
By the way, Dr. Freeman still here until next week. And yeah, at the end of next week. Tomorrow we'll have a workshop in building 59. Next week we have one seminar, same in this room. And also we will have one more workshop, also in building 59.
If someone would like to speak with me, please write a letter to Professor Sayed. So please, and you will hear too, because I will be here. And I will be happy to share my knowledge with you because it's one of my goals. Thank you.
Which office you are?
Say it how you can find the office.
Which office?
You can send to the public.
CI office.
I'm sure I can see it. That's cool. Thank you.
Thank you. Very nice. Talk.
Oh, that's great.
Yeah, of course. Oh, man. Whatever. Cheers. A lot. Yeah.
Y el pues seguimos. Ahí, pero sí es interesante. Se decía que mecánica y uso no quieren modelar, por ejemplo, un motivador con un coeficiente muy elevado, porque si no el coche va a tardar mucho en regresar. Tampoco puede ser más, es más rápido. Entonces ahí tienes que encontrar como una función que se regrese de la manera más estable posible de estar el potencial del coche. Entonces es interesante. De hecho, inicialmente mi área de interés era en eso, liberación mecánica, control de vibración, ya sabes. Pero luego entré a la industria, que cambié de área. O sea, mecánica, porque pues porque es parte del tema, ya sabes. O sea, lo tengo que estudiar. Entonces, no, o sea, yo tengo la parte teórica, pero ya si quería ir más allá, ya tenía que ir a la maestría. O sea, pero aquí entiendo las bases.
Bueno, la parte más
I was the manager of the he's even understand the reason to understand. I can give a sample.
You're still here. Planning to work on the outside.
Oh, that's yeah, how can we find the slides of the material?
No, okay, I will share.